Yeah, hello, everyone. Today, I will continue to teach about electric potential energy. I started this topic on Wednesday. And first, I would like to review very briefly what was done on Wednesday. But first of all, I hope you can hear me.
Yes, we can, sir.
Can you confirm? Yeah, thank you very much. So last time on Wednesday, we concluded that a particle which has charge, when it moves in an electric field, the potential energy of that particle having charge will change. So whenever a charge moves in an electric field, the potential energy, electric potential energy change. And that change of potential energy we designated by letter delta U. Delta means the difference between final position and initial position of the particle. And that change of electric potential energy we calculate as the negative of the work done by the electric force. And the work done by the force is given by this line integral, F dot ds from initial point A to B, and electric force F is equal Q times E, where Q is that charge which is moving in the electric field, and Q is constant, so I can take Q in front of the integral. So that's the expression now, general form of expression, which you can use to calculate the change of potential energy of that charge when it moves from point A to B. So this is the line integral. So you see, we integrate over that electric field, which can change from point to point in terms of magnitude and in terms of the direction. So that vector line integral is, can be quite complicated to calculate, but few examples will be given later on today. So that's how you calculate the change of potential energy when that charge Q moves from point A to point B. And as you see, the change of potential energy depends on the magnitude of the charge. So if the particle has a lot of charge, then the potential energy is large. So clearly, change of potential energy depends on the magnitude of the charge. Of course, it depends on the electric field as well. Now, that negative sign, as I was explaining to you, is very important to keep because that negative sign assures us that the change of potential energy will have correct sign as well. So when the charge Q, positive charge, moves in the direction of the field, potential energy decreases. When the charge moves in opposite direction to electric field, potential energy decreases. And that change of potential energy is then important to calculate. Remember that only change of potential energy is meaningful, and change of potential energy can be positive or negative. Potential energy, of course, is a scalar quantity, and we measure it in joules, but the change of potential energy can be positive or negative. So if potential energy at point B is smaller than at point A, delta U will be negative. But if potential energy at point B is larger than at point A, then delta U would be positive. So that much was done more or less last time. And because that change of potential energy of the charge Q depends on charge Q, then it is useful to define a quantity which is independent of the magnitude of the charge. And that quantity which is so useful is called electric potential difference, which we designate by letter delta V. And that electric potential difference is defined as the potential energy delta U divided per positive charge Q. So as you see, potential difference is defined for positive charge. Remember, there are positive and negative charges, and we have to decide, and physicists decided that now delta V will be defined as the change of potential energy per positive charge, when positive charge moves from place to place. So if I substitute delta U, for delta U, this expression given by this integral, I will animate in a minute, but I still can, now I can get to animation. So So this, yeah, so I substituted this quantity here for delta U, and then as you see, Q cancels, Q will cancel, and potential difference, electric potential difference, delta V, is then given as the negative of that integral of electric field E dot ds. So this is the line integral, vector line integral. That negative sign must be there because delta V, electric potential difference, can be positive or negative. So it can increase, or the potential can increase or decrease, and the negative signs will guarantee to us that our calculation of delta V are correct. So, so of course, we spent a lot of time about electric potential energy and electric potential difference in physics 1801. So all these expressions should be now familiar to you. So remember that delta V is just amount of energy per unit charge. Why I say per unit? Because if Q is equal to 1, then delta U divided by 1 is delta U, and delta V is equal to delta U in terms of magnitude if Q is equal to 1. So delta V, we say, is the change of potential energy per unit charge. But remember that delta U is measured in joules and delta V is measured in volts. So these are two different quantities and have different units, but they are very closely related through this important equation, that delta V is equal to delta U divided by delta Q. So today we will be calculating the change of electric potential, delta V, for different electric fields. And once you calculate the potential difference between 2 points A and B, then if necessary, you can calculate change of potential energy if the charge Q would move from point A to B, because delta U then would be equal Q times delta V. But remember, Q can be plus or minus, positive or negative. So we have to always remember to take the sign of the charge into account because delta V was defined for positive charge. So if Q is negative, then we have to insert here a negative sign. So all of these things were done in physics 1801, and we did practice. We spent quite a lot of time about electric potential energy and electric potential difference in physics 1801. So that was, so any questions so far about this slide? So hopefully everything is clear. And so let us now then calculate the electric potential difference for between 2 points A and B in different electric fields. And the first example is to calculate the electric potential difference between 2 points in the field, electric field produced by line of charge. So here you see that you saw that image long time ago, many times before. There is line of charge, and let's say if the charge on the is positive, then that positive charge on the line will produce electric field, which is in terms of direction radially away from that line of charge. And the magnitude of that electric field is given by this expression. So that was derived, this expression was derived in two different ways, by using integration and using Gauss law. That electric field is given by this expression where lambda is the linear charge density on that line of charge, and r is the perpendicular distance from that line of charge. So let's say that we have here a line of charge in cross section, and in that plane of the screen, electric field you see is radially at perpendicular direction to that line of charge, and the magnitude of electric field decreases with the distance. So here vector is large, smaller, smaller, because I wanted to indicate that electric field decreases as 1 over r, it decreases with the distance. And we want to calculate electric potential difference between 2 points, between point A, let's say here, and point B, somewhere here. So let's say that the distance of point A from that line of charge is r with subscript A, r with subscript A, And this distance to point B is designated R with subscript B. So we will do calculations parametrically. So what is the potential difference between any 2 points, A and B, in that electric field produced by line of charge? Let's say if that would be now very long wire, charged wire, that would be that wire would produce this static electric field. So the electric field is given, and we have to evaluate this integral. And that point A and B are located on the radial direction. So on one of these radial directions from the line of charge. Okay, so in 3 dimensions, maybe this would be point A, and you go along the same radial direction and get to point B. So that was point A and point B. So integration will be along that straight line from A to B along that radial direction. So that's how you evaluate that line integral. So, because under the integral, we have the dot product. Electric field is a vector quantity, which is now written here. This is the magnitude of the electric field. And I added the unit vector r hat. That unit vector I added to remember that the electric field is radially away from positive line of charge. Radially, r means unit vector. So this is nice expression now written for electric field as a vector quantity. Vector has magnitude, and the direction is specified by that unit vector r hat. Now, because my integration will be also along the radial direction from point A to B, as I've explained, then the displacement, the differential displacement ds, I can write all like this, dr r hat, which signifies that the integration is also, that the displacement from point A to B is also along radial direction. That's why I put the unit vector r. So then the dot product, E dot ds, dot product, you see both quantities, electric field and the displacement ds are in the same direction. So the dot product is the product of these 2 quantities because they are parallel, right? These 2 vectors are parallel. So the dot product will give me EDR cosine, which I didn't write, cosine of 0. Cosine of 0 is 1, so I didn't write that cosine of 0. Cosine of 0, which is equal to 1. So this can be written, the dot product can be written like, that constant 1, 2 pi epsilon naught lambda divided by r dr. So this is my integrand function. So here delta v will be equal that integral. I substituted now this, of course, here, and I can take now all constants in front of the integral. Lambda is constant, of course. Epsilon naught is constant. Pi is constant, so I take constant in front, and then the integral is trivial because dr over r is ln of r, and then you have to substitute upper limit, and then minus ln of the lower limit. So this is the expression, and then I combine these 2 logarithms. Ln of rb minus ln of ra is ln rb divided by ra, and this is now the general expression of the potential difference of voltage between 2 points, point A and B, in that field produced by the line of charge. So that's how you do calculations. The case was pretty simple because my integration, of course, was along the direction of electric field. So that was relatively simple integral to evaluate. And that expression which we just derived will be used in the future lecture. So you don't have to memorize it, but at least this is the example how you calculate the potential difference between 2 points in a field produced by the line of charge. So any questions so far?
Yes, so my question is, what happened to the r hat when you multiplied it? Because it just disappeared like after.
Yeah, so it disappeared because the dot product, as you remember, the dot product between 2 vectors are like this. If I have dot product E dot ds, the dot product is equal to this. magnitude of vector E, magnitude. Remember, magnitude is always positive value. So I write here absolute value E times magnitude of ds, magnitude, it's always positive, times cosine of the angle between these two vectors. In my case, that angle is 0, so cosine of 0 is 1. So here I have to multiply E dot ds, right? So that's how I evaluated dot product. And now E is, magnitude of E is that much. Magnitude of ds is that much. dr, I call it dr because integration will be along the r direction. And that's how that now unit vectors disappear.
Okay, thank you.
Yeah. In the future, probably in next week, probably on Friday next week, I will introduce the spherical and cylindrical coordinates, and we'll do some calculations and calculate electric potential difference between 2 points for more complicated cases using spherical and cylindrical coordinates. Why I mentioned cylindrical coordinates? Because for that field produced by the line of charge, that electric field, of course, is easy to describe in cylindrical coordinates. Cylindrical coordinates, because that field has that cylindrical symmetry. So, but the only coordinate which you need here is that r. We don't need remaining two cylindrical coordinates in this case. So what I'm trying to say is that next week on Friday I would explain more details about cylindrical coordinates, and then this notation here will be a little bit more clear. But it should be clear even right now. You see, what I did, I have written that electric field in terms as a vector, electric field is a vector quantity. It has magnitude and direction, and that unit vector represents just the direction of electric field, right? So this is the unit vector is in that radial direction, and then my displacement, because integration will be done along the radial direction as well, I have written also as dr r hat, also in radial direction. And the dot product is what? So these are r is really coordinate in cylindrical coordinates, right? That's one of the coordinates in cylindrical coordinates. And then the dot product is the first coordinate times the first coordinate. Okay, there are no other coordinates, because in cylindrical coordinates, you need three variables, r, say phi, and z. So these are cylindrical coordinates. But in here, that phi coordinate and z does not change. Phi would be this angle, and z would be this direction along the line. But my integration is along the radial direction, so I didn't need phi and z. So that would be explained next week if you are confused. If you did not use cylindrical coordinates so far, I would be shocked by that. But if you did not use, then wait until next week. So I hope that was my long answer to your question. Any additional questions? If not, then I will do another example. So let us do this example, because last week I was explaining about coaxial cable, and remember we calculated electric field in the coaxial cable. So here you have that inner wire of radius A and outer shell, metal shell with radius B. And when we use Gauss law, we concluded that electric field is present between that inner wire and outer shell, and that electric field is radial in that region, goes radially away, and magnitude of that electric field is given by the same expression as electric field due to line of charge, which we did on the previous slide, right? So that's what we calculated using Gauss law. This is the electric field. So electric field is the same, it goes radially, right, between inner wire and outer shell. And I want to now calculate what is the potential difference, what is the voltage between that inner wire and the outer shell. So I want to integrate to find that voltage or potential difference. Potential difference is a proper term between these 2 points. This is maybe point A on the surface of the wire and point B on that inner surface of that shell. I want to integrate of that electric field from that point A to B. So I want to evaluate that integral. Now, because electric field is given, we calculated that previously using Gauss law. Delta S displacement, again, I will take the integration along the radial direction, like that red line here, radial direction, so that displacement delta S I can write as dr r hat, like for that line of charge. And then the dot product, like for the line of charge, is equal EdR times cosine of 0. And I substitute for electric field. So this expression is the same, of course, as on the previous slide. So the potential difference between inner wire and outer shell of the coaxial cable, we will calculate in the same way as on the previous slide, because this expression under the integral is the same. So the result would be, again, the same. Negative lambda divided by 2 epsilon naught ln of BA. The only difference is that radius here I designated by B and the other radius by A, B and A radius. So that's how you calculate potential difference between the inner wire and outer shell in coaxial cable. And again, we will talk about coaxial cables in the future lectures on a number of occasions. And we will be using that the result, delta V, potential difference between the wire and shell of the coaxial cable in the future. So that's the same calculations as you see as for the line of charge, because electric field in that region between inner wire and the outer shell, in that region, electric field is also radial from the wire, and magnitude of that electric field is due to that just inner wire. So any questions about the coaxial cable and potential difference voltage between inner wire and shell of the cable? Okay, if no questions, then let us do the third example. The third example is to calculate electric potential difference between 2 points, point A here and point B, but located in the field produced by a point charge. Here I have positive point charge, but the charge could be also spherical charge, because remember that electric field due to point charge or spherical charge outside of the sphere is given by this expression. So this is due to the sphere of charge or point charge, 1 over 4 pi epsilon naught Q, magnitude of that charge, divided by R squared. And electric field is again radial, in radial direction from that charge or the sphere of charge, radial direction. So I put R hat so that electric field I could also write as a vector, see? So electric field has, again, magnitude, and direction is specified by that R hat, radially away. So this electric field produced by the point or spherical charge, you see only here electric field lines in this plane of screen, but the electric field, of course, goes in all directions in space. That electric field has spherical symmetry. So it is convenient to use, of course, spherical coordinates to do calculations. But because my integration will be along the radial direction, I just use only one spherical coordinates, R. But I will explain more about spherical coordinates on Friday next week. But for now, integration will be along the radial direction. So we are given the electric field, which we calculated previously, of course, using Gauss law. And of course, that was also done in physics 1801. So you know very well that electric field given by the point charge, the spherical charge is given by this important expression. But right now, we will then calculate what is the potential difference between 2 points, A and B. And let's say that the distance of point A is given by that RA, subscript A, and point B, distance from that charge capital Q is given by this symbol R with subscript B. So what I have to do, I have to evaluate this integral. between these 2 points, A and B. So electric field is radial. Displacement, delta S, I can again write as dr r hat. And electric field has magnitude E and r hat. So these 2 vectors, electric field and displacement, are parallel. So yeah, cosine of 0 is 1 because these 2 vectors are parallel. So angle between them is 0. So r hat times r hat is 1. Right? Because now maybe that was the question so if you would have dot product r hat dot r hat, what is that dot product? Well, the dot product is this. Magnitude of r hat is equal to 1 because that's the unit vector. So magnitude, the length of that vector is 1. The magnitude of the second unit vector is also 1. So 1 times 1 times cosine of 0. Cosine of 0 because the r hat and r hat are 2 vectors which are the same vectors, parallel. So cosine of 0 is 1. So here you have 1 times 1 times 1 is equal to 1. So r hat times r hat is equal to 1, of course. So that's why r hat disappeared. That was the question students asked me on the previous slide. So yeah, so integration is here again very simple because electric field is just dependent on distance r. So the only variable is r, and I can take again all constants in front of the integral, so negative q divided by 4 pi epsilon naught, and then integral 1 over r squared is equal to negative 1 over r. We did this type of integrals before on few occasions. And then I substitute upper limit and lower limit. Okay, but this negative sign and this negative sign gives me positive sign. Minus and minus give me positive. So it would be, this is the final expression of that potential difference, that it would be q divided by 4 pi epsilon 0 r with subscript b minus q over 4 pi epsilon naught ra. So if q is given and r, b, r, a are given, you can calculate potential difference between any 2 points in that field produced by a point charge. And each of these terms we designate by letter v, and we call it electric potential at particular point in that field produced by the point charge. So this is, you see, each of these terms is called electric potential, designated as V, not delta V, but as letter V. So this is so every point around the charge, if you have a charge, every point in that electric field will have certain potential, and that is how you calculate potential, electric potential at every point around the point charge or spherical charge. So remember, electric potential is a scalar quantity; it has just magnitude, right? But you should remember that this electric potential depends on the distance r, not r squared, but distance r. And if q is positive, potential will be positive. But if q is negative, then v will be negative as well. So potential v can be positive or negative. Positive charges produce positive potential, negative charges produce negative potential. So that was all done in physics 1801. And again, we spent a lot of time about these concepts. But here I wanted to demonstrate to you that we evaluated this integral, this line integral, to get this expression, which we now call electric potential. So any questions regarding this slide?
Hello, Professor.
Yes.
I was just wondering, what makes this slide different from the previous one?
Well, the previous one, this is a very good question, actually, because in the previous slide, we considered the coaxial cable. And coaxial cable, as you remember, has that inner wire, which is like that pen, which I hold in my hand, and surrounded by that cylindrical shell, right, which is made of metal as well. But in that region, between the inner wire and shell, electric field is radially away. So you see, electric field would be, if I could take, so the electric field is now indicated by the pen. In different directions, that electric field is radially, but in 3 dimensions, you know, like this. But when you have a point charge, let's say if this is, I don't have any little sphere here, but but let's say if I don't have any really suitable, but imagine that this is little thing, which imagine this is like a point charge. Then electric field goes in all directions, in every direction in 3 dimensions, radially away. What you see on the screen here is the cross section of that electric field, right? So in the plane of the screen, electric field goes radially away, but electric field due to line of charge is fundamentally different from electric field produced by a point or spherical charge, because for the line of charge, electric field goes radially away. You know, like maybe I could go back to this slide. You see, here's this. I showed that image to you so many times here that you remember this. This is the line of charge, and electric field is radially away in all directions, right? Perpendicular, always perpendicular to the line of charge. So this is the illustration of that electric field. But electric field due to a point charge goes in all from that point charge in all directions, in 3 dimensions. So I don't have now appropriate image to show you the 3-dimensional electric field of the point charge, but I hope you know what I mean. So the electric field due to line of charge of the electric field in that coaxial cable and electric field due to point charge, they are very much different in terms of now directions and in terms of magnitude. You see, magnitude of electric field due to point charge or spherical charge is given by this expression. This is the magnitude. It depends on r squared, 1 over r squared. But electric field due to line of charge, remember, was dependent just as was given by this expression. So electric field is 1 over r, where lambda is linear charge density, 1 over r. Okay, so these are 2 different electric fields. So you should not be surprised that the electric potential difference between 2 points in the field produced by line of charge or in the coaxial cable and in the field produced by point charge or spherical charge are so much different. So I'm not sure if that was your question, but your question allowed me to clarify a few points about these 2 electric fields. Did I answer your question, by the way?
Yeah, you did. Thank you. Thank you,
Okay,
Professor.
thank you very much. So yeah, so as I've mentioned, every point around the point charge will have electric potential given by this expression, which I just explained. And you have to remember that the positive charge will produce positive potential, but negative charge will produce negative potential. So potential can be positive or negative. And of course, when R is very large, when it goes to infinity, then electric potential approaches 0. So we say that electric potential at infinity is equal to 0. So if you plot, I didn't include that plot, but if you would plot potential due to positive charge as a function of R, that potential would increase as 1 over R, like this, right? So if you get closer, this is dependence 1 over R, hyperbola, 1 over R. But if the charge is negative, then the potential it decreases like this because it's negative, right? But at infinity, 0. So quite often we say that we measure the potential relative to infinity. So in static equilibrium, the field produced by point charges, we measure relative to infinity. So because at infinity potential is 0, so that's a convenient reference level. And then at any other distance, r from the charge, potential is given by this expression. But remember, it can be positive or negative. Although V is scalar quantity, but it can be positive or negative. So all of this, of course, I was explaining in physics 1801, So this is just a review. So if you want to calculate electric potential due to many charges at a certain point, let's say if I have 3 charges, Q1, Q2, Q3, and let's say if all charges are positive, then the total potential at this point, maybe I call it point P, you have to use superposition principle. You have to calculate potential due to each charge separately. So this is potential due to charge Q1, which is a distance R1 from point P. Q2 would produce its own potential given by this expression. Now R2 is the distance from Q2 to point P, and Q3 would produce also its own potential at point P, given by this expression. So you have to calculate total potential due to many point charges, you have to use superposition principle, remembering that if the charge is positive, you take plus. But if the charge is negative, then you have to substitute, let's say if Q3 is negative, then this term would be actually negative. If Q3 is negative, then this, instead of plus, it would be minus, right? So you have to remember about that sign. Again, we did all that work in Physics 1801. Any questions? Yeah, if you don't have any questions, then I would like to now, I would like to calculate electric potential not due to point charges, but due to continuous charge distribution. And when charges are continuously distributed, like the charge on the rod or charge on the surface of the sphere or on the plane, then the electric potential we have to calculate using integration, or like this, that we have to divide that charge into many tiny pieces and then integrate over the entire charge distribution. And I would like to illustrate how to calculate electric potential due to continuous charge distribution by using simple example. The rod, actually we did this example in Physics 1801, but imagine that you have the rod, which is positively charged, let's say. So the charge on the rod is positive everywhere, positive, that the charge is uniformly distributed on that rod, and that the total charge on the rod is Q, and the length of the rod is L. So here you see it. The total charge is Q on the rod, and the length of the rod is L. But I want to calculate electric potential at point P. Let's say this is my x-axis, and let's say this is my y direction. The rod is positioned along the x-axis, and I want to calculate potential at point P, which is a distance a from the end of the rod. So this is distance a. So to calculate potential due to entire rod, I have to do integration, because remember that this formula V is equal K Q divided by R. This is only valid if Q is a point charge or a spherical charge, You cannot use this expression if charge has continuous charge distribution, like on the rod or on the ring or something like that. Then you have to divide, like in this case, we have to divide that ring into tiny chunks, tiny parts. One is indicated. Let's say the length of that tiny chunk is dx, and the amount of the charge on that little element is dq. Then this little chunk of the rod produces potential at point P, and that potential at point P, due to that tiny chunk, is given by this expression, dV, that differential amount of potential due to that differential amount of charge, dq. And remember that now dq should approach 0, should be very tiny, so that this little chunk we can treat as a point charge. And then if we treat this little chunk as a point charge, then the potential produced by that point charge at point P would be dV, tiny contribution to total potential dV, would be equal K dq divided by the distance. And this would be the distance. So this is the distance, which I called R. I could call it X, maybe that would be more convenient. Let's call it X. So this is my distance X divided by X. So we use now superposition principle. Then I would have to take another little element of the rod, calculate potential due to P. Then another little element, calculate potential P, which means that we have to find the sum of all these contributions to the potential at point P, which means that we have to integrate both sides of this. So the total potential due to entire rod, you could find as K, which is constant in front of the integral, dq divided by X, where X is this distance from the chunk to point P. So maybe I actually, to be more consistent with what I have written on this on that slide, maybe I should actually, because here I have written, I see that V is I'm using that R. So let me call this distance X. This distance X, although on the screen, okay, so yeah, I'm sorry, I changed. Now actually in this particular solution, we designate by X this distance. Okay, I will clarify. So X is this distance. This is the X from the origin. This is Y, this is X. And here I designated by X this distance. And in a minute, I show you how to calculate if X would be from the chunk to point P. Okay, but in that solution here, X is from the origin to that element dx. So with that designation of X, then the total potential, and this distance is designated by letter R. This is distance R. Then the potential, due to that little chunk, I would write dV is equal K dq divided by R, which is the distance from point P to that charge, which the amount of charge here is dq. Okay, and then the total potential would be equal K integral dq divided by R. So I would integrate over all these possible distances R. So that's what is written here. But you see the distance R, I can express like this. Distance R can be written all like this. The distance R is actually equal to L plus A. You see, if you add L plus A, that would be this distance. This is L plus A. L plus A minus X. So R is equal L plus A minus X. So if you substitute this for R, then you get this integral to evaluate. Right? I substitute for R L plus A minus X, and instead of dq, I have written lambda times dx, because if we designate that linear charge density lambda is q divided by L, then dq would be lambda times dx, as we did many times in previous lectures. So instead of dq, I have written lambda dx. And now this integral would have to have limits, because my variable now is x. So the limits of integration would be from the smallest value of x, which is this chunk at this end of the rod, that x would be the smallest, to this point, where x then would be equal to L. So limits of integration would be from 0 to L. And if you take the constants, k and lambda are constant in front of the integral, then integral which you have to evaluate is of that type, dx divided by L plus A minus X, and this is a trivial integral from 0 to L. How do you solve these integrals? By substitution. So if here you substitute u is equal L plus A minus X, then du is equal to negative dx, because L and A are constants. So then you can change the variable from x to u, and this integral will become now, instead of dx, you write negative du, because du is equal negative dx. So dx is equal negative du. So negative du. I know these are trivial for most of you calculation, divided by u, right? Of course, I would have to change the limits of integration as well. And this integral is just negative ln of u, where u is equal L plus a minus x. So this would be equal negative ln of L plus a minus x. So that's how you evaluate this integral, which is written here. And then you substitute upper limit for x and lower limit for x, and you combine these two logarithms, and this would be the electric potential at point P. We did these calculations previously in Physics 1801. So that's how I did this calculation on this slide. But because I was initially using this as x, so many students, I'm sure, would ask me to ask, what if I designate this distance by x? Not like here, but if this is my x, how would you set up integral? Well, you would set integral in a similar way, that the total potential is then equal negative k. And so all of this would be k dq divided by the distance, but distance now of that element of that charge to point P, I designate by x. So divided by x, because x is the distance now. And instead of dq, I would write again, why did I write negative? So that should be plus k. Instead of dq, would write lambda dx divided by x. But the limits of integration would be, you have to integrate over x now. And the smallest value of x would be when you take this element at this end. And the smallest value of x would be equal to what? It would be equal to a, because this distance is a. So the limits of integration would be from a to the largest value of x when the element is at this end, and then x would become L plus a. So plus L plus a would be the upper limit. Okay, so that's how you would set up integral if you designate this distance as x. And the final result would be, of course, the same. It would be k ln of x, and limits of integration would be a plus L plus a. So when you substitute, then of course you get this result, the same result. Okay, so I clarified that you can, of course, designate the variable in two different ways in this particular case. So any questions? Yeah, well, again, we did these type of questions in Physics 1801. So I would like to move forward. I will do a few more examples how to calculate electric potential due to different charge distributions in tutorial on Wednesday next week. So I'm skipping a couple of slides right now because I will do some more examples in tutorial next week. But what in the remaining time, which I still have about almost 10 minutes, I would like to now do something different, which we did not do in Physics 1801. So I was just explaining to you that we can calculate electric potential difference between any 2 points, A and B, in any electric field by evaluating this vector line integral, right? And a couple of examples were given on previous slides. So this is how you calculate potential difference if the electric field is given. But then the question arises, can we calculate electric field if we know how the electric potential change in space? So if we know electric potential, let's say if I know how electric potential depends on x, y, and z in space, because electric potential can change from point to point, right? And in general can depend on x, y, and z coordinates. If I know this, can I calculate electric field? That's the question. If I know electric potential, can I calculate electric field? And the answer is yes. And from application point of view, that's usually how we do it. That first we calculate or measure electric potential as a function of x, y, and z. And when we know electric potential, then we calculate electric field from that potential. And once we know electric field, we can calculate force, which is equal Q times E. So that's how we do it actually in most applications. So right now, I would like to then explain how to calculate electric field from the potential, if we know electric potential. So please listen carefully. So this integral, we can rewrite in differential form like this, that differential change of potential is equal negative E dot ds, right? And because electric field, I can always write in component form as x component I vector, unit vector plus y component j plus z component k, right? Any vector can be written in component form like this, where ex, ey, ez are components of vector E, and ij and k are unit vectors. Ij and k are unit vectors in xy coordinate axis system. And then displacement ds, the differential displacement ds, can be written also in component form as dx I plus dy j plus dzk. Right? So that was explained actually on Wednesday as well. So then the dot product E dot ds, including that negative sign, remember negative sign is important, can be written all like this. The first component times the first component. Dot product, you evaluate first component times the first component plus second component times the second component, third times third component. So here I have rewritten, I keep the negative sign and I have the sum of products of these components, ex dx, ey dy, ez dz. Okay, so that's how I have written dot product in terms of the components. But dv, the differential dv, it can be always written or using the Taylor theorem like this, that dv can be written like this, dv dx, because remember, I'm here assuming that electric potential depends on y, x, y, and z, that it changes, and that we know that function, that we know how the potential change in space, that we have certain expression, maybe it could be like now x squared minus 4yz, something like this, okay? Like I'm making it up right now, but we have explicitly expression, let's say, how the potential depends on x, y, and z. So if we know that function, how potential change in y and z, then any differential dv can be calculated as the partial derivative dv with respect to x. This is partial derivative, which means that here y and z you keep constant. This is partial derivative with respect to y, so you keep x and z constant, and this is partial derivative with respect to z, so x and y are constant. So I'm pretty sure that you know that any differential, any change of the function can be written in 3 dimensions like this. That I'm sure was done in physics in calculus 1014, and it will be done, of course, very thoroughly in mathematics, not in physics, but in mathematics 2015. Now, for a single variable function, if you would have just v as a function of x, or in general, if you have any function f depending only on x, like a single variable, then as you know that df can be written as df dx times dx, right? That in single variable. But in 3 dimensions, you have to add these 2 terms. So this is based on Taylor theorem. So I'm sure that you are familiar with this. So so on the one hand side, so this is dv, which is left hand side of this expression, and the dot product we substitute by this. Dot product substitute by this. So if I compare now these 2 expressions, that this must be equal to this left hand side equal to right hand side, then this equation is valid if it's valid if, so I have rewritten this expression again, and this is correct if ex is equal to this dv dx, of course, remember about this negative sign. If EY is equal negative dv dy, and EZ is equal negative dv dz. So you see, so this is, and remember that that V is the function of X, Y, and Z. So that is the way how you calculate then components of electric field, so that the total electric field can be written all in unit vector notation as X component I, unit vector EY, J, EZ, K. Here I substitute for EX these partial derivatives, and that's how you find electric field if you know electric potential. So this is very important expression, which will be on the next test number 2, and on the final exam, I guarantee to you. So this is how you calculate electric field if you know electric potential. And usually we write that expression in kind of a shorthand notation that we define this del operator, which is designated by that inverted triangle. That del operator is defined like this. You see that d dx I hat d dy j d dz k unit vector. So then with this designation, then electric field is written as negative del of v. Del of v. Well, del operator is this operator, and I show you how to use that del operator in on Wednesday, in the lecture on Wednesday. But for now, I just derived it. So that electric field can be calculated, we say, as the gradient, because the del of that scalar quantity. Remember, V is a scalar quantity, not a vector quantity. So this is called the gradient. Electric field is called is the negative gradient of the electric potential V, where of course V, remember, depends on X, Y, and Z in general. Is a function of these three variables. Okay, so I am not sure if you have learned about the gradient in calculus 1014. Can somebody, or calculus 1013, could somebody tell me whether that gradient operator was defined in calculus 1013 or 1014? Could you please tell me?
Sure. I learned that this year in 2015.
Or 2015. So looks like that gradient operator was not covered in 1013, 1014, but it is, of course, covered in Mass 2015, which all of you either took before or taking this semester. So the student was telling me that now the del operator was actually defined in calculus 2015. It has been already defined, right? Could you confirm that? Did you take that 2015 this year or last?
I'm in it right now. So
right now, yeah. So that was done. So you should know it very, very well. So what a good synchronization between calculus and physics. So yeah, so I repeat again, you can calculate electric field as the gradient of the potential. That's a significant thing to do. Because what we do in practice, you see, in practice, we usually calculate electric potential because potential is a scalar quantity. So it's very easy to deal with electric potential because it's scalar quantity. Once we calculate electric potential as a function y, z, then electric field, we calculate as the gradient of that potential. Okay, so that's one way to calculate electric field from the knowledge of electric potential. So we will be practicing this type of calculations next week. I just introduced this concept right now, but because the lecture is now finished, so I will stop recording, and I will review all these concepts again on Wednesday next week, because on Monday next week is the test number 1. So please make sure that you are very well prepared to write the test on Monday. And I posted announcement about test number 1 on eClass. All of you should read that announcement so that you know what to expect on test number 1 on Monday. So I will stop recording right now, and I will be staying a little bit longer.